Alright, so in this video I'm going to be explaining another article for domain adaptation, and the problem is in unsupervised setting, and the measure that we are using for a problem of domain shift is maximum mean discrepancy. But a version of maximum mean discrepancy, we call it weighted MMD. So the title is called Mind the Class Weight Bias. So this article in 2017. In domain adaptation, maximum mean discrepancy has been widely adopted as a discrepancy metric between the distributions of source and target domains. However, existing MMD-based domain adaptation methods generally ignore the changes of class prior distributions, class weight bias across domains. This remains an open problem, but ubiquitous for domain adaptation, which can be caused by changes in sample selection criteria and application scenarios. We show that MMD cannot account for class weight bias and results in degraded domain adaptation performance. Because sometimes we have a class prior, for example, some labels have more frequency, so it should be fair. Otherwise, the classic MMD does not work properly. So to address this issue, a weighted MMD is proposed. Specifically, we introduce class-specific auxiliary weights into original MMD for exploiting the class prior probability and source and target domains, whose challenge lies in the fact that the class label in target domain is unavailable. To account for it, our proposed weighted MMD model is defined by introducing an auxiliary weight for each class in the source domain. Any classification EM algorithm is suggested by alternating between assigning the pseudo labels, estimating auxiliary weights, and updating model parameters. Extensive experiments demonstrate the superiority of our weighted MMD over conventional MMD for domain adaptation. So you see the class prior distributions for digit recognitions. We have more 1 and 2. For example, in street view, we have more 1. So it's natural to see that the class weight 0 and 1 are relatively high, 0 and 1, in postal services, for example, in street view or postal services. And the class weight of 1 and 2 are relatively high in the house number, high in the house numbers, street view house numbers. So 1 and 2 are high in street view house numbers. So this is the results of minimized MMD and weighted MMD. Because if you just use MMD, you have this problem. But for weighted MMD, you have better performance. And you see samples of class 1. First, I should say this is the source, and we have class-wise weighting, and this is the target, so it has a better performance. And we will see the performance later. But due to unavailability of labels in target domains, one commonly used strategy of unsupervised domain adaptation is to learn domain invariant representation via minimizing the domain distribution discrepancy. Maximum mean discrepancy is an effective non-parametric metric for comparing the distribution based on two sets of data. Given two distributions S and T, by mapping the data to a reproducing kernel Hilbert space using function phi, the MMD between S and T is defined like this. So we have source distribution, target distribution, and we have this. But this expectation denotes the expectation with regard to distribution S. And phi, norm of phi less than 1 defines a set of functions in the unit ball of a reproducing kernel Hilbert space. I have a video about reproducing kernel Hilbert space if you search on YouTube. So denote by D sub S and D sub T two sets of samples drawn IID from distributions S and T respectively. An empirical estimate of MMD can be written like this, because now phi are just the feature map. But if you know about kernels, you can simplify this. So K is usually defined as the convex combination of L basis kernels. So your MMD can be written like this, which is a sum of these kernels and negation of these kernels. So the calculation of MMD is very simple. Metrics for domain discrepancy. Besides MMD, there are several other metrics for measuring domain discrepancy. For example, distribution matching embedding, where both MMD and the Hellinger distances are adopted to measure discrepancy between source and target. Instead of embedding of distributions, discriminative methods such as domain classification and domain confusion have also been introduced to learn domain invariant representation. However, class weight bias is also not yet considered in these methods. Several sample reweighting or selection methods are similar to our weighted MMD in split and have been proposed to match the source and target distributions. These methods aim to learn sample-specific weights or select appropriate source samples for target data. Different from them, our proposed weighted MMD alleviates class weight bias by assigning class-specific weights to source data. So we will introduce the proposed weighted MMD. So PS, PT are probability density of source and target, and Y sub T is the class labels of X sub T sub S. Sub S and X sub T. Actually, both PS and PT can be further represented as mixtures of class conditional distributions. Because we say, what is the probability that this label is selected? So as you see, it's a mixture of different probabilities, different weights of different probabilities. And so this is prior here. So this PSYS and PSYT, are class prior probability of source and target. And the difference between class conditional distributions and this PT of XT conditional YT serves as a proper metric for domain discrepancy. However, due to unavailability of class labels for target data in unsupervised domain adaptation, the MMD between those two distributions is usually adopted as a domain discrepancy metric. But when the weights are equal, we argue that it is a suitable alternative. Unfortunately, the assumption does not hold. So MMD cannot cope with class weight bias across domains. We propose to construct a reference source distribution. This is called the reference source distribution for comparing the discrepancy between source and target domains. Specifically, we require that PS has the same class weights with the target domain, but owns the class conditional distributions. So just select alpha C to be the fraction of W target with respect to W source. So in order to eliminate the effect of class weight bias, we put this alpha as linear combination of these probabilities. So we are trying to eliminate the effect of class weight bias. So DS is a training set from source domain, DT is a test set from target domain. And given the class weights of the target samples, the empirical estimation of weighted MMD can be written like this. And of course, we can always write it using kernel functions. But you see the difference. Now the change, you see some weights. So that's why we call it weighted MMD. And then you minimize this loss. You minimize this loss and MMD here and loss of source and target as usual. But this is weighted MMD. So we explain the optimization procedure of proposed model following the CEM algorithm. So we have expectation step, E step, we're estimating the class posterior probability of X sub j. And the C step is assigning pseudo labels and estimating auxiliary weights. And we have M step as well, updating the model parameters. Given the model parameters for each X sub xt, for a target, we first estimate the class probability based on the output of softmax classifier. The pseudo label to yj is assigned to X, that target sample, based on maximum posterior probability, and auxiliary weights are then estimated based on pseudo labels. So given yj and alpha, the conventional backpropagation algorithm is then deployed to update the model parameters W. So the details of E step and C step are here, and of course M step. For E step, we fixed W for each sample from target domain. The CNN convolution neural network output to the Thies class is represented as G sub C. Here we simply define the class posterior probability. In the C step, we assign pseudo labels to that target. And one is the indicator function. But in M step, we fix alpha. The subproblem on W can be formulated as this minimization problem for the source, loss for the target, and the weighted MMD. Since the gradients of three terms in this loss, in this minimization problem here, are computable, W can be updated with mini-batch stochastic gradient descent. And Z sub I is quadtuple, and the else layer feature represents of Zi. Given Z sub I, the gradient with respect to else layer parameter can be written as. So we get the derivative, and then taking k equal to 1, for example, it can be computed like this. But you can also calculate this for other k-values. Thus, the model parameters can be updated via backpropagation with a mini batch of quad tuple. So you see, if your source is A and you go to target C, you have different accuracies for different methods. For example, for AlexNet is 84, but for this method of this paper is 91%. But in order to have a fair comparison, we always take average, because some of source and target domains are good, some of them are worse. So it's better to have average in your paper so that the outlier could not force you or could not judge. So this is this paper, and this is the performance in different methods, class weight bias. You see, as class weight of airplane target domain increases, the accuracy decreases.